Welcome everyone. It's a pleasure to have Alfredo Guevara in the second part of the three-part lecture series with Uricol. He's a BHI fellow, one of our very own, and we're looking forward to your talk. Alfredo, please.
All right, thank you. Thank you for the invitation, and I hope to live up to the standards that we have set in the previous lecture. But
He's watching you.
Yeah, we'll do what we can. We'll do what we can. Also, I know many people are in the meeting in DC, so I will try to make it sort of Zoom friendly, and hopefully the recording will not be so messy. So this part two will deal with also aspects of duality, but mostly integrability. We will try to understand what integrability means in the context of black holes. So we have a very nice introduction in the last lecture. And let me just sort of motivate you. Of course, there's no motivation needed in this audience, but just to sort of get back to the point of integrability and duality, there's this very nice quote, and actually a nice article by Robert Discraft, who was director of IAS for a little time. After there was the observation of the Event Horizon Telescope, it was released. Robert Discraft wrote this very nice article, sort of making the comparison with the sort of atom in the last century. Of course, the motivation is that this thing was the black holes were sort of theorized. They were suggested by the theory. They were sort of taken more seriously over the time. There was some experiments that were proposed, and they were finally verified. And now we live in an era where we are actually very, very lucky to count on at least two interferometric experiments, such as, of course, the Event Horizon Telescope, and also LIGO, these the ones to come. So the name of the game in this era is to come up with accurate predictions for astrophysical black holes. And we know that rotating black holes populate our universe, and they are strongly believed to be described by the Kerr metric. So this is a little miracle that we can write this closed compact formula to describe these beasts. So this is a closed form solution of general relativity, and it has been tested to high precision. Now, let me just introduce the syllabus of this course. So in part one, we had some aspects of the hydrogen atom, and we also saw some parts of the dion, and we know that duality in gauge theory relates these two things. And we want to understand what duality operates more in the gravitational side, and Uri also explained to us more or less how that is operating. Of course, there are still some questions there, but in this part of the lectures, we will focus on this character here that we will call the self-dual black hole. Now, the self-dual black hole shares many features with Kerr, which is the one that we care about, and in particular, we will see that hidden symmetries. I didn't want to spoil the diagram here, but obviously it's connected to the story of hidden symmetries of Kerr black holes, and also to conformal symmetries, such as the ones that I will describe. And after understanding the symmetries, we will jump in the third part in more sort of phenomenological aspects of what we can compute with these things, and we will deal with the wave equation and the geodesic equation. And also, hopefully, I will kind of cover a little of the program that we're currently exploring with Uri called the twistor theory. So one question you may have is, okay, why is this the end goal? Why the wave equation and the geodesic equation are our absolute objective? Well, it's because we can observe the some implications of the wave equation in many different contexts. So here I try to sort of sketch the spectrum of what's called the sort of a Conan approximation. If you're not familiar with these concepts, don't worry. The only thing we need to know is that we have a solution of the wave equation in Kerr spacetime. That's called the Teuchowski equation, as we reviewed in part one. And this equation controls certain modes of the black hole. So in particular, we can solve this wave equation. We find that there are some of metastable states, there are decaying states, After long times, they have some imaginary frequencies, so they decay, and they show up in this nice sort of aftermath of a black hole merger called the ring down. And indeed, it's a very sort of key signature of black holes that you find in these quasi-normal modes. In particular, if you have wormholes and things like that, you will essentially see other sort of quasi-normal quasi-normal modes in the sort of ring down spectrum. So, for instance, at late times in the black hole merger signal, you will detect some of these deviations from these quasi-normal modes. On the other hand, once we write this solution, right? So this is this wave equation that we solve in the Kerr spacetime. We can take some limits. The sort of physical way to understand this, we take these geometrical optic limits in which waves become or behave as particles. So we take sort of the large frequency limit, or in some language we take the higher harmonics of this wave, and what we find is that essentially the wave function behaves like the classical action, and that connects our solution of the wave equation with a solution of the geodesic equation. Right, because now by the WKP method, you may be familiar, we can write a particular trajectory, a classical trajectory, and identify it with the sort of argument of this solution. So I actually should include here factors of H bar here. So as we know, the geodesic equation shows up in the particular solution to understand the photon ring. And so indeed, these same quasi-normal modes that we observe in the ring down, but taken to higher and higher harmonics, are the ones that we will measure after we trace back to the photon ring. Because these are essentially the modes that decay, that are stable, sorry, that are unstable, but they orbit a few times and then they just decay, right? So those are exactly the sort of geodesics close to the photon ring. But indeed, we can solve this equation at any L. So we can solve it at finite L or large L, and both of those regimes have information about the black hole. Okay, so we know that Kerr is a closed form solution, but we know that at the same time that the wave and geodesic equations are not closed form solutions. Indeed, almost by definition, we call the wave equation a Hoyne equation, which is a very complicated second-order differential equation that we don't have a closed form. But there is a contrast to this statement, which is that in classical mechanics, the sort of analogous problem of bodies orbiting other bodies, right? So we call it the two-way problem. You can think of a massive body or a small body orbiting a big black hole. They are in the classical regime. They are completely solvable with elementary methods. So you don't need to look out or define your new differential equation, call it Hoyne equation or whatever. You just solve it using essentially Euclidean geometry. So essentially, if you are some Greek in the old times, you can indeed sort of figure out more or less what's the mathematical equation that describes the motion of two bodies. Now, why is that? Well, why can we solve this problem? Essentially, there is something called the Laplace-Runge-Lenz vector, and this vector happens to be a symmetry in the sense that it's conserved. The Laplace-Runge-Lenz vector, you can visualize it in this ellipse, is essentially aligned with the major axis of the ellipse. So the fact that it's conserved means that this major axis doesn't deviate, right? So that when the axis deviates, we call that precession, and we know that in real life things precess. But in this particular Kepler problem in classical mechanics, this vector is conserved, so there's no precession. Of course, you can try to sort of compute it geometrically. There's a sort of vector pointing outwards, and then there's the radial direction, and they just align perfectly with this coefficient here. K is related to the Newton constant, so that you get essentially the direction of the axis. And this is not a mathematical coincidence. In fact, even the simplest quantum mechanical system, call it a hydrogen atom, so this is how we connect these two things, was indeed solved by looking at this Laplacian length vector. So this is a paper by Pauli. I don't know any German, but I think it says something like solving quantum mechanics or solving the new quantum theory with symmetries or something like that. Does anyone know any German?
It sounds like that.
It sounds like that, yeah. It's like solving quantum mechanics. I think this is even before, as you mentioned.
So, Alfredo, you said it's not an accident. But if I looked at general force laws, it's only 1/r² that gives this property, right?
Right.
Any other power, it will start processing, and I presume this quantity is not conserved.
That's
Okay.
true. Yeah, that's
So
true.
it is something that's related to the particular shape of the force law.
Yeah. So, okay, we could delve into the decay rates and try to analyze it from dimensional analysis. There is something related to the scale here and to the dimension that's going to be very important, which is essentially an emergent conformal symmetry, is what dictates that there is a Laplacian length vector. And people knew that the hydrogen atom has something conformal on it, even though they didn't express it mathematically until later. So let's try to sort of step back a little bit and think about ellipses generally. So again, if you are some Greek mathematician and want to understand why planets move in ellipse, you should come up with a theory that tells you that the ellipse is a solution. So this is one proposal. So suppose that you indeed define a vector. This vector, we call it L. Of course, it will be related to angular momentum, but it has a particular deviation that goes with a parameter alpha. Okay. So I should explain what alpha is later, but for now, let's call it the diamond charge. Okay, so now this particular angular momentum vector is pointing in some direction, and you can compute, computing dot products. I presume Greeks knew how to compute dot products. You can indeed show that R, your position, is lying on a particular cone, center along the direction of your angular momentum. So we should modify this. It is supposed to be L. Right. So now your R lies in this cone, and that just comes from the definition of L being a constant. Now suppose there's another constant. That constant we call again the Laplacian length vector, and it's given by a similar expression, but instead of R cross P, you have P cross R. And also there is some term proportional to this diamond charge. Now, when you compute R dot, some combination of the Laplacian length vector and angular momentum, you find that again, you get a constant back. Now, if you consider these two equations, right? So the first one is a cone, and the second one, because there is no R hat, so that's the sort of mathematical point here, there's no R hat. This one is indeed a plane, because it actually bounds the norm of this vector. So indeed, you need to solve these equations by intersecting a cone and a plane, right? And that indeed happens to be this ellipse. And now you can ask, okay, what is this space where these vectors live? It's not actually space-time. We will sort of cover that in the third part, but it's sort of a fifth-dimensional sort of space-time that I kind of constructed so that I can play this image. But the mathematics that are operating here, in a sense, are higher dimensional. So there is some conformal symmetry operating in this higher dimensional spacetime that allows you to construct these vectors. Now, you can of course, the reason that this happens is because these two vectors are constants. Okay, if they were oscillating, what you will find is that essentially this ellipse will start rotating, right? It will start rotating because this A vector will just move around, so the cone will intersect different plane. So there you can sort of estimate the sort of periastron precession or the perihelion precession if it was a planet, essentially by computing the time average variation of the LRL vector. If it's not conserved, it will just fluctuate. Okay. Now this is all very nice in the sort of classical motion. But what happens with the quantum theory? Let's say what happens with the wave equation, right? So now I'm trying to solve some wave equation in this space-time, which is the Tarkovsky equation. So I will just remind you what the implications are of concept quantities. These are very general statements. So if I have a wave equation, what I have to solve is something like this, right? So my Hamiltonian is my wave operator. This could be the Tarkovsky equation in a Kepler space-time. And I need to find the eigenvectors of this Hamiltonian. So I just try to diagonalize it in some basis. But if I only have one eigenvalue, it's going to be a little hard. So I need to sort of find my basis by imposing new quantum numbers, right? And the way I choose quantum numbers in quantum mechanics, I need to find operators that commute with each other, so that I can label all these numbers simultaneously. And I try to sort of diagonalize all these operators at the same time, right? So if I have three components, like three concept quantities, I try to diagonalize each one of them at the same time as the Hamiltonian. So what I end up is something that looks like sort of products of eigenfunctions for each of these labels. But perhaps there is a degeneracy in the sense that maybe there are many states that have this label. So I need to sort of fine thread a little bit more. But in the simplest case, it's supposed there is no degeneracy. So I have these quantum numbers. I solve my wave equation with energy and momentum, or whatever you like to diagonalize. How is that related to the previous problem? Well, we know that A is a concept quantity. In the previous case, it was a Laplace-Rungelen's vector. Now, when you have a concept quantity, the classical action indeed becomes separable, because you can always find sort of these action angle variables such that the classical action can be expressed as a combination of these angle variables, very generally defined, times this conserved quantity. So in particular for the energy, we know that the classical action develops a constant part or a proportional part to time. Right? This is the so-called Hamilton principal function. And if you have 3 or 4 concept quantities, indeed you can completely separate the classical action. And from the previous analogy, we know that in some limit, in this equal limit, this wave equation is related to the classical action in this way. And what you get is essentially separability, because now you can just factor out all the sort of pieces of this classical action into time and angles. So I hope that kind of makes sense. But in any case, the message is the same. You can sort of factor out your Hilbert space in the quantum numbers of these labels. You can factor out your classical action in the concept quantities of these symmetries. The language may be different, but the implication is essentially the wave equation and the geodesic equation are essentially intimately connected. Okay. But again, they are very hard. So indeed, the geodesic equation has solutions in terms of elliptic functions. This is courtesy of our friends, Sam and Alex. And we know that integrating these elliptic functions, takes centuries of hard working, and we know we can put it in the computer in some ways, but requires some approximations and so on. So indeed, even if you know the wave equation or the geodesic equation, either way you're kind of trapped, because these either way are sort of non-closed form expressions, and you need to eventually resort to some other non-elementary methods. So let's just follow for a second this law that the black hole is the 21st century atom. Okay, so again, the 20th century atom was indeed proposed, and it was analyzed. The first one was with the hydrogen atom. The spectrum was solved. It was solved exactly. People were happy, and then more complicated systems appear. But if the black hole is really something like this, or if we are modeling these black holes theoretically, we should start by modeling something very easy. So we should ask, okay, what is the sort of textbook example that I should solve if I take a course on general relativity before jumping into all these Kerr black holes and Churchill and complicated Coin functions. So I'm going to ask if there's any example of black holes I can solve by elementary functions. And that means that I'm asking if there's an integral sector, relativistically, not like in the Kepler problem. And in that case, I'm going to ask also what are the implications for the two-body problem. Okay, so now what I'm going to do is I'm going to give you some clues, and some of these clues might be obscure, depending on what your background is. So some of them may not make any sense, but at least one of them should at least resonate with things that you have seen before. I presume that this one may ring a bell because it involves something we usually do when we solve geodesics in Kerr or other spacetimes, which is resorting to this Carter constant. Okay. So there's a concept quantity that was not supposed to exist. If you just look at the Kerr black hole, there's no enough symmetry for another concept quantity. Let me just remind you that you have symmetry in time and in angle, time phi, but this C is unrelated to either of those. So there is this sort of tensor, right? So this is Killing tensor that satisfies some equation called the Killing equation. And then essentially what you do is you take this Killing tensor and you take your Hamiltonian and you commute them and you find C, okay, as differential operators. So this is actually a very long computation. If you were to write it as operators in the wave equation, but if you were to compute geodesics, you would replace your nablas by p's and replace your nablas by p's here, and then commute with some Poisson bracket, and you will still find zero. So in the wave equation of the geodesic, these things commute, and we go back to the story that these are conserved charge. Now, why is there a conserved charge? Why is there a Killing tensor? Well, that's something also we discussed briefly in last lecture, but there's no sort of intrinsic derivation of why this thing is there.
Sorry, but this is true very specifically for 4 dimensions. It's not a general, thing that happens for anything that has event horizons or black holes within general relativity, right?
What is true for specifically?
They're killing Yano tensors and hidden symmetries.
Oh, you're asking if there's killing. You're saying that you're asking if killing tensor exists in higher dimensions.
No, I'm not asking. I'm just saying that this is very specific only to 4 dimensions.
Even more, it's very specific to Kerr.
Yeah.
Well, it's stationary. The statement is stationary. It's not Kerr. Yeah.
Okay, that
Kerr, you mean with
yeah.
non-uncharged? Maybe.
But there are type D spacings and type 1 spacings that have this. So it's not, and in 4 dimensions. So it's not just curve.
yeah.
That is what I mean,
Yeah,
but
exactly.
Uri said only Kerr. I think it's general type. Yes,
Right.
Okay,
it's general type, but
yeah.
this is not, so for the geodesics and so on in higher dimensions or within theories of general relativity, this is only valid in 4 dimensions.
I guess the existence of a Killing tensor. I'm not an expert in higher dimensions. I understand. The statement I'm familiar with is close to what Prashant said, which is any type D spacetime has a Killing spinor, which eventually turns into a Killing tensor. You can associate that with the Killing Yano tensor. I'm not telling you exactly how to construct this. I'm not sure the converse is true. I'm not sure if any Killing tensor comes from a type D spacetime, but at least that's one constructive way of getting this. Of course, type D spacetimes are particular to 4 dimensions, so maybe that kind of resonates with.
I think there's a way of generalizing the idea of a Killing Yano tensor. There's something called a conformal Killing Yano tensor in higher dimensions. But this is very specific to 4D.
Right.
Yeah.
Right.
Alfredo, one more question. I'm not familiar with the Killing Yano tensors in for the wave equation. Do they depend on So the spin of the perturbation.
Very good question. Very good question. Indeed, the Killing tensor doesn't depend on the spin of the perturbation, right? But the wave operator does depend on the spin of the perturbation.
So C will depend on S, but K will not. Is that right?
C will depend on S. Yeah. Indeed, even in a geodesic, forget about the wave equation. You take a geodesic orbiting a black hole, and if the particle that's orbiting the black hole has a spin, the conserved quantity is not the Carter constant. Indeed, it's a combination of the Killing-Yano tensor. So what's intrinsic is the Killing-Yano tensor, right? The Carter constant is just the fact of scalar particle in good question. So the existence is miraculous because it just allows us, it's just the right thing that we need to separate the geodesic equation, and per my previous argument, also the geodesic equation. Okay, so let me just show you the result. Of course, you already saw this from Uri's talk, but just to recap, this is self-separation between angular and radial equation in Kepler. So that's what the Killing tensor buys you. But despite this sort of miracle, okay, we have this, but again, I should sort of repeat myself once more, these solutions are not closed form. So again, we are in trouble. But again, these are just clues. I'm not giving you a statement or a theorem right now. The second clue comes from something that people have very recently understood, at least far more recent than the existence of the Carter constant, which is a story that has to do with conformal symmetries. Now, the Killing tensor itself is related to some conformal group, but there's a particular conformal group that arises in the near sun region of a black hole. So what does that mean? You have to go to some definition here in terms of the frequency of your wave. So I'm not really going to delve into that. Let's just think of the black hole as having roughly 3 suns. One sun which I'm really close to the horizon. That's going to be near sun. Another sun that's going to be really far. That's the far sun, and sort of a buffer sun in between the two, where I can sort of match my computations as if I was computing sort of a boundary condition in between the two. So one of the reference for this sort of matching procedure is given in this paper by Andy and company. And indeed, they show in that paper that after you consider this constraint, meaning in the phase space of the wave at low energies, you will find an emergent, meaning not given by the black hole itself, but an emerging symmetry of the wave equation, which is SL2R plus SL2R. Now, I will explain what SL2R, how it operates in a second. But essentially, it's a new symmetry because it wasn't there from the space-time. Okay, and the third clue is related to the previous one, but it's a little more specific in terms of applications. Now, these conformal symmetries tell you that if you are going to solve your wave equation, you should try to diagonalize your wave operator, but you should also try to diagonalize the symmetries, right? So if you have a symmetry, you want to find the representation. In the previous case, that wasn't the case. Indeed, there was a problem with the generators of the symmetry that were not globally defined. But in this case, very recently, very recently indeed, I have the reference here. People have managed to use this symmetry to construct actual solutions. Okay, so define a symmetry that's completely regular in the region that these vector fields live. Using that vector fields, you can construct a representation, and when you analyze this representation, you find that the solutions have a particular behavior, called the law of symmetry, and indeed you can constrain what's called the love numbers. Now the love numbers, I'm not going to go into that. There's a whole story. Also, Maria here is the expert, but there is a particular sort of black hole tidal response after you throw in a wave. So you use this Telkolk equation to solve this sort of tidal response of the black hole, and you find that the black hole is rigid, so it has no sort of response, no tidal deformation after you throw in a particular perturbation. And this has been explained using these particular generators here. Again, constructing the solution of this perturbation. Okay, I'm gonna skip this part. The only reason I typed in this slide is just to show you that SL2R is a particular algebra, and the generators are defined this way. They satisfy such a sort of this is the structure constants of this algebra. Important thing is that these SL2Rs don't talk to each other. So these are two separate copies. Now, SL2R is the conformal group in some particular signature. So let's just review. Let's just very briefly review what SL2R
Question.
is. Yeah.
So you mentioned there was a problem with global versus non-global.
Yeah.
Right. So you're choosing the local sort of hidden symmetry, DSL. This is what you're going to do, right?
No, so far I'm just giving a small overview.
Okay.
In the love symmetry story, there is a global generator. In this other hidden symmetry story, there's local generators.
Yeah, but okay. So about this one here, there are two proposals here. There's another one. So
Right.
Misha and Al is one option for
Yeah.
global definitions, and there's another one
Yeah.
in there. But then when you're doing the Kirchhoff-Natt description, you're not doing any of the global ones. That is what okay.
Hold that thought for
Okay.
a couple of slides. I will jump into Kirchhoff-Natt hopefully by the end of the talk.
Okay, it was
But it's a chain that I cannot obviously give a complete overview of the whole literature. As you said, there's different groups working on this. But the sort of message is that there is some conformal structure that appear, over and over in this business. So Kerr itself has no conformal symmetry apparently. Neither does the hydrogen atom, but over and over we're coming back to this business that there is some particular hidden symmetry that only appears in the wave equation or in the geodesic equation, but it doesn't show up just from looking at the metric. Now, this may or may not resonate with you, but I need to sort of review at least sort of basics of the conformal group. Not even the basics, maybe it's just definition. The important point that I want to notice is that usually when we talk about conformal group in two dimensions, we talk about some transformations on the sphere, that the sphere has a Euclidean signature. And that sort of conformal group is SL2C globally, is defined as 6 generators that satisfy some commutation relations. That happens to be related to the Lorentz symmetry in 4 dimensions. A way to understand it that goes back to the work of Dirac. This is called the embedding formalism. You think about your Minkowski space-time, and then you ask, okay, how does the Lorentz transformation look on a particular time slice, right? So you take some proper time slice, some Cauchy slice if you want, and ask what does the Lorentz transformations do? Well, some Lorentz transformations will just start rotating, in the sphere of this Minkowski spacetime, right? Those are just rotations. And some Lorentz transformations will boost your vector, but in boosting your vector, they will keep you in the same slice. So this slice, which geometrically is some hyperbolic slice, it's H3, it stays where it is under the action of the Lorentz group, right? So all you can do is that you can sort of conformally map this slice to itself. In that way, we understand that the Lorentz group in 4 dimensions happens to be the conformal group of this hyperbolic clear space. And in fact, it's actually the isometry of this hyperbolic clear space. Now, there's some particular story as well for the sort of space-like slices. I'm not gonna, obviously, it can be understood similarly. But sort of the point I want to make here is that there is an SL2C in the Minkowski spacetime that we understand very well. But sometimes, and I say sometimes, big quotes, because it depends what you have in mind for applications. And keep in mind that I do sometimes high energy. It's more convenient to use SL2R cross SL2R instead of SL2C. And the reason that, these factors and this one doesn't. And indeed, this is the Lorentz group, but it's the Lorentz group of a different signature, of a signature plus plus minus minus that we call Klein signature, essentially because Klein actually discovered this even before Minkowski. But he got a minus sign from, fortunately. So in Klein signature, there is something very similar happening. There's a conformal group acting on these slices here. These are DST slices now. And yeah, pretty much you can essentially do the same game, but the asymptotic structure is completely different. We don't call it Minkowski space, we call it Klein space. The both, if you want, the icons are all connected, so there's only one non-infinity. So things are a little different, but the structure of the conformal group is the same, or at least algebraically the same. Okay, so after that brief digression, I hope all of these words in part 2 already kind of resonate with you, except for the self-dot black hole. But we have looked into Kerr. We have seen that there's hidden symmetries such as the Killing tensors, and we have also seen these conformal symmetries emerging from the wave equation. So is there any question before I move on? Okay. So we want to explain, or we would like to explain, the origin of the conformal structure and better understand where it's valid. We will show that the symmetry is exact in the sense that it's not an approximation of some particular region of the wave equation in this particular solution that we call the self-dot point. And that the self-dot point, and this will be in the part of the third lecture, is quite literally the hydrogen atom. For that to be true, we need to understand exactly what the hydrogen atom, how does the equation for the hydrogen atom look like. So that's why I'm not describing it today. And finally, we will argue that even from this self-dot point that it's integrable and we can compute the wave equation, we can sort of separate back from the self-dot solution to we can deform it to recover the sort of astrophysically interesting solutions, which is of course the Kerr black hole. So it's like you take your hydrogen atom and say you turn on a magnetic dipole, and then it becomes non-integrable. But you can sort of compute the Zeeman effect, and you can compute the sort of degenerate spectrum after you turn on this magnetic dipole, or if you turn on the hyperfine structure constant, and so on. In this sense, the sort of Kerr solution is some sort of fine structure deformation of the self-dot solution.
Is that statement true for like low spins or in general?
Low spin.
Okay.
Low spin of the black hole.
Yeah.
Good. Yeah, that's a very good question. The statement is true in general, but the sort of accuracy of the approximation, how many orders you need to compute, that is really, I think, is really sensitive to the spin. That's one thing that we're a little confused right now. But that is a very good question. Okay, so what is the self-dual circle? Well, indeed, we already defined what self-dual, or at least what duality means, right? So duality is the thing that rotates the sort of plus and minus components of your your sort of gauge field or your metric. Indeed, he showed how to do it in terms of the curvature tensor. And then you can ask, okay, what's the point that doesn't rotate? So in a real metric, you know that the plus and minus are conjugate, so they will always rotate. But in a complex metric, you can allow yourself to solve this equation. Okay, so you can sort of project out one of the helicities. So in this case, you take the plus, and you project out the minus. And this has a very nice interpretation in terms of the S matrix, which may or may not be of interest to you, but indeed there is. I will explain what this positive helicity means in a second. But sort of historically, and let me backtrack a little bit to what's the history of this thing. People were not really interested to solve, duality problem in general relativity. People wanted to compute solve points of padding integral of quantum gravity and look into instanton solutions, BPS monopoles, all kinds of solutions that you can write down in a Euclidean padding integral. Okay, so nothing to do with astrophysics. However, it was quickly developed as a mathematical field on its own, and in particular, there is this very nice definition of ALE spacetimes that were addressed in the 70s and 80s. And the sort of mathematical interest happens because these are essentially the gravitational analog of the gauge theory instantons. So in the same case, similarly to the Dirac string in gauge theory, the solution here will have some other string called the Misner string, which is the gravitational analog of that solution. But the fact that you have the strings, this Dirac string or Misner string, tells you that the solution has some conical deficit, and so maybe it's not interesting for astrophysics. But we will see that there is some way out. There is some particular interesting setup, and indeed this setup happens to not be studied at all, or not very much. So let me just describe what is this solution. So a fairly general solution of this self-dual equation is due to Plebanski. It involves, as Maria was mentioning, the spin parameter, the mass, and the net charge. Now, if you take the net charge to 0, you get care. Okay, so now that makes us all happy. But if you don't take it to 0, it's still not that bad because there is a deformation that's very simple. And indeed, in some particular coordinates that I won't write here, it's just a linear deformation. In this case, it enters, in the location of the horizon, so it's a little tricky, but you can sort of gauge it away and sort of write it very simply, so some linear perturbation. But in the case that it's non-zero, what happens is that you have some conical deficit in the time, in some angular direction, in some azimuthal direction, and you don't like that because conical singularities are a problem. So people would say, okay, you need to deal with some particular defect in your space-time. Maybe proceed with caution. And that has been the law for a while. People still want to understand this. But one observation we made very recently with Andy and Erin and Noah here in the Andy's group is that if you go to 2,2 signature, okay, so going back to that discussion about the conformal group with 2,2 signature, these things are way simpler and there's no Misner string. Okay, so that's the takeout. If you think about 2,2 signature for a second, there's no Misner string. You have to do some analytic continuation, but all this problem about the conical deficit is gone. Okay, so let me just try to briefly sort of cover a little bit more self-dual point. I'm trying to trigger your interest here in self-dual gravity. It's a trending topic right now. There was a conference last week about self-dual gravity, essentially. So trust me, it's gonna be a big topic in the next year.
Yeah. A question on the previous slide. So here, these transformations in the previous slide, where you mentioned t goes to it and all that.
Yeah,
so,
okay, my computer seems to get started.
So if you were to do this for Schwarzschild, switch signature, you presume you can do that, right? Like you can go from minus plus 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 to plus minus minus plus plus. Would you use the same set of transformations, or is this something different?
Oh, let me answer that while I try to fix my computer.
Okay.
Because it seems to have some technical issues. Yeah, actually,
You need a different computer.
yeah, maybe I can connect to you. Sorry about that. Then I share screen. Good. Thank you so much. Okay, so yeah, in the Schwarzschild case, I mean the Schwarzschild case is contained in this case, right? Yeah, this is the most general Levansky solution, and the only thing you need to be careful is you rotate time. There are things that are both pseudo vectors that if you sort of do a sort of parity transformation goes to t goes to it, you need to essentially rotate anything that has d over dt, right? So the angular momentum or the angular velocity rotates with that. The not charge is some kind of angular momentum too, so it rotates. So that's kind of the rule.
Sorry, follow-up question.
Yeah.
I should not have said Schwarzschild, but how about Reason-Ostrom? Would you have the similar set of transformations?
Yeah, we haven't looked at this. I guess the only thing we need to make sure is that the result is a maximal extension. Yeah, but we haven't looked at this. But because Q is not really a pseudo vector, I think it should not rotate. But it's a little tricky to find these transformations. Actually, there are many ways to rotate. Actually, I should be more careful. There are many ways to analytically continue things to Togama 2. But this one is good in the sense that it gives you sort of maximal extension of the space. Yeah. Okay, so again, what's the cool thing about the subplot point? Well, phenomenologically, you have two polarizations for your gravitational waves. You have linear polarizations, as you know. You can choose a circular basis for them. And as I said, projecting to the subplot point is killing one of the gravitational waves. Now, if we think about particles for a second, so let's think about gravitons. Okay, so gravitons are these quanta of gravitational waves. What we're doing is that gravitons have two states. They can be up or down, just like electrons. And we're killing one of them because the coupling of such a graviton to a black hole happens to be proportional to this combination m plus n, right? So as I tune m to be minus n, I decouple my graviton from my theory. And indeed, I just keep this sort of positive helicity gravity. And I can see that essentially because these gravitational waves are given or are described by these two scalars. These are called Leibniz scalars. We can compute them in gravity in gauge theory. So now comes the beautiful thing. So these self-dual spacetimes, for the reason I just mentioned, are called half flat. Okay, so they have no curvature on one side, and they can be constructed from twistor space. Okay, this is a very, very nice theorem of Penrose and Todd, who was his collaborator, and it's very nicely summarized in this beautiful paper that has now been revisited by the sort of string theory community and so on, because it shows up in very different aspects of holography. Of course, I'm not going to talk about that, but let me just mention that Penrose here very nicely described some objections to the way we're doing quantum gravity or quantum mechanics. And he's saying that essentially you cannot consider linearized fields, okay? So our way of describing general relativity in terms of gravitational waves as being linearized perturbations, even the Taukovsky equation I showed you, he's saying that's wrong. You need to consider the full nonlinear perturbation of a metric. And I'm going to show you that full nonlinear perturbation satisfies a very simple sort of linear looking equation. So that's kind of his main point here. And just to quote him a little bit, he's saying that for a pure graviton in a helicity state, we would apparently require one of the components of this Weyl tensor to vanish. And he will refer to this sort of case in which one of the components vanishes as either right flat or left flat. And then he's proposing a single left-handed graviton described as positive frequency right flat complex space-time. So a graviton itself now is a space-time, not sort of a perturbation or a linearized gravitational wave. So in that sense, these space-times are nonlinear graviton. So okay, then he goes on to say that this may be somewhat mysterious. Why are we considering these space-times? But then it so happens that they can be constructed automatically from twistor theory. And okay, then he does some advertisement of twistor theory. And some of that happened to be true, some of that didn't turn out as he expected. But indeed, the things that turn out as he expected is that using twistor theory, we can indeed compute many things, and we not only compute this operation here. Let me call it the 1-point amplitude, right? It's just how I couple one graviton to my black hole. We can compute 2-point amplitudes. We can compute. We can construct. We can. We can compute. Yes, there's a lag. So we can compute two gravitons coupled to the same black hole. Okay. So this is something that you can do with twistor amplitudes. So with twistor variables, it's really easy. It's a 2-line computation. This is nice paper by Atul, who is a PHI fellow here. And I don't expect you to look at this formula in detail, except for the fact that it has two components, two momentum, right? K1 and K2, which are the momentums of these two gravitons. And there is something nice of this formula, which is that it tells you that there's quantization, and it tells you that in this black hole, the spectrum of waves is integer, is quantized, and it tells you that there is stable solutions which do not precess. Now, I can skip this part, but if you are sort of familiar with this argument, maybe you will appreciate it. Although I'm not saying it's a formal argument, but if someone gives you these things, these 2-point amplitudes, you can just essentially look at the poles, and you can see that there are some solutions of the wave equation that oscillate or decay, just by looking at the poles of this function. So the fact that you have sort of integer poles, okay, tells you that most solutions, or the solutions that scatter in this black hole, are not decaying, okay. And that's very important because it tells you about stable solutions. In the geodesic, this would be a stable geodesics that they just don't fall into the black hole. And these are the ones that people usually call quasi-normal modes. In the case of astrophysical black holes, in this case, are called normal modes.
So you see this from the Paul structure formula?
Yeah, you see it from the Paul structure, but again, I didn't want to go into this argument too much. But analytically, we know that these functions have the structure of bound states in the complex plane. But yeah, that's that. Yeah,
but that's not immediate from the formula.
It's not immediate. It's not immediate. Yeah. Okay.
But did you say it also doesn't precess?
Yeah, it also doesn't precess. Good.
It doesn't make sense. I mean, we know that test particles want to precess, right? So these are not test particles. These are something else.
Particles in this self-flow black hole don't precess, essentially because there is a Laplace-Runge aspect.
Oh, because it is self-dual, so Mercury will not precess.
Yeah.
Ah, okay, I didn't get that.
Yeah. Good. Yeah. So okay. Sorry, I should have mentioned at some point maybe we started talking about self-flow black holes, and then I'm not gonna say it anymore. all of this is self-dual.
Now it is self-dual, okay.
Okay,
This is not taking the limit of the curve
No.
solution, okay.
Well, it is in a sense. Sorry, I should say, when M is N here in this curved tau knot solution, it is the self-dual black hole. Right? When N is 0, it is curved. When A is 0 and N is 0, it's Schwarzschild. So the case we care about is N equals M. Okay, for now. For now. But we will go.
So Schwarzschild, if you add some N, you will no longer have precession of Mercury.
Yeah.
Okay.
Exactly.
Okay.
Exactly. Now you can ask, how does the precession depend on N? And it depends very mildly on N. So indeed, you can estimate using perturbation theory how this precession operates.
It doesn't depend on the sign of N either.
Oh yeah, that's a good question.
Sign of what?
N.
I think it's there should be a symmetry to flipping the sign, right? It's like
Yeah.
flipping the sign of A.
This is so strange. Okay.
Yeah, this is a really good question. Yeah. Yeah, I think it depends.
I guess you need to do both. You change the time direction and say in that
Yeah, I think it's equivalent. It's not.
it's minus t, and then because you have squares, it sort of flips everything.
Right. Yeah, N goes to minus N, it's like T goes to minus. I have to be very slow here. Okay, so again, this suggests, and again, in the case of the self-dual black hole, that we can solve the geodesic exactly, and perhaps we can even solve the duality problem. Okay, by which I mean we can consider two genetic mass ratio compact objects in the self-dual theory. Perhaps we can find a closed form exact solution for such a problem. And we have a very strong hint from brilliant mathematicians here at and Hitchin, who indeed found a two-body solution that is not static, it doesn't have a time-like vector of the self-dual gravity. Now, the interpretation of this Atiyah-Hitchin space remains to be decided, so the jury is still out. But at least we have different clues coming from different aspects of formal theory that there is a particular solution. Okay. So we will analyze. Okay, I maybe I oversell a little bit. What we are after is just the geodesics for now. The duality problem seems to be the next step. But in terms of the geodesics, we can say a lot of things if we analyze the conformal structure. Okay, so now we're gonna jump into the story of conformal symmetry.
So one more question.
Yeah.
There are approximations here because you're not allowing gravitational radiation.
Oh, very good. There are solutions which are self-dual and they are radiative.
They are radiative, right?
They are okay. So once we take Einstein theory and we impose the condition of there is only one mode, right? We kill the negative helicity gravity. We kill one graviton. We say this is a particular equation that people solve, and it has many solutions. One solution is has form of a plane wave, so it's a particular sort of radiative plane wave. This solution has no radiation. The one that Atiyah and Hitchin described, and the one that I'm talking about, the self-dual black hole, has no radiation. This is stationary.
But is that something that you put in, or are you saying that the solution just pops out and says there is no radiation?
The solution has, okay, so we don't know what's the most general solution. We know certain solutions according to the symmetry. So if we impose, a spherical symmetry, we have some solutions, and we know all of them. If we relax the assumption of spherical symmetry, then we have radiative plane waves.
I see.
So we don't know all of the solutions. We know particular cases. Yeah. So that's why this question of what's the duality problem, it's interesting because from the solutions we know, it seems that there is no radiation. but we don't know all the duality solutions. Yeah, thank you for that question. So if this helps me, okay. So
We are getting time.
all right. Oh, what? Oh, yes, good. Sorry, yeah. All right, yeah, we can finish here. All right, yeah, okay. So this story may resonate with some of you. It's a story of conformal coordinates. I don't expect you to look at this in very detail. This is part of the paper we're putting out very soon with Uri. But let me just emphasize that there's a coordinate transformation that has these parameters, okay? N and A. N is not charge and A is the spin. And after you do this coordinate transformation, so you go back to that very complicated Boyer-Lindquist knot solution, you do this coordinate transformation and you end up with this one line solution. It has no spin. So the spin parameter has been absorbed by the coordinate transformation. That is something that only happens in the solvable sector. There's only one, in a sense, there is only one self-dual point. There's no spinning black hole or a static black hole. They are the same up to a diffeomorphism. And indeed, they are even more than that. They are a particular symmetric space-time. This helps me. Come on.
Automatically.
All right, there we go. Almost there.
But you keep going. It
Right.
won't stop.
Right, the next one. I'm gonna jump to the next one immediately. Yeah, I don't know. It's really fun.
So here, are you talking about a general n, or is n still equal to n?
M equals to n.
N
M
equal to n.
equals to n. The spin parameter can be completely absorbed.
Yeah.
And that's the result of this paper with Andy. And indeed, there's more, and I wish I could explain detail, but these metrics are very, very simple and they are very symmetrical. They are related to twistor story, and I will cover that next time. But the important point I wanted to exhibit here, also related to Maria's question, is what is this sort of near horizon approximation that we saw? It has this conformal symmetry. People knew that there is some conformal symmetry in Nickel black hole as you go close and close and close to the horizon. Well, in this case, indeed, if you try to go close and close to the horizon, you end up in the same point. You don't really do any approximation. Indeed, the black hole itself already has enough symmetries to account for this conformal symmetry. So you can say in that lore that the self-dual black hole is its own near horizon. So really that is hinting that there is no different regions in this black hole. It's just one sort of solid thing. If that makes any sense. And just to sort of make it more precise, there are a particular symmetry group that you can write down for this black hole.
What is the symmetry here? Is it the SL2R times SL2R what you're picking, or is just the exact?
It's an SL2R which is exact. It's an isometry of the black hole.
Is it like a U1, SL2R times U1?
Right. Yeah. That's right. It's a full U2. That is the isometry even with the spin. So you still have this U2. And then there's a hidden symmetry which is also exact, which is another SL2R.
Does it become an enhanced thing, like an SL4,2 or something?
Great. Now we're going into the last. We will see how it enhances to SL4,2. Yeah, great. That SL4,2 is also SL4, which is a symmetry of twistor space.
Correct.
So that's why we want to make it twistor-like in the next step. Yeah. Okay, so just to finish with this discussion, just to sort of circle back to the original motivation, which finding this Laplace-Runge-Lenz vector. What is this Laplace-Runge-Lenz vector in general relativity, not in the Newtonian Keplerian problem? Well, maybe I miss you in the previous slides, but you should maybe not notice that there were three quantities called sigma 1, sigma 2, and sigma 3. I may risk going back, but maybe not. Okay, here they are. No, go forward one more time. Okay. There is sigma, okay, pay attention because you're gonna have one. So there is sigma 1, sigma 2, and sigma 3 in this slide here on top. Okay, these are one forms. These are very important because they rotate under the isometry group. So the SO3, which is this rotation group, is part of the isometry group, rotates these things around. Now, if this helps me, that structure, that there is a triplet that rotates under this SO3, sort of translates to a particular triplet of Killing-Yano tensors. So as you start with these sort of one forms, you can also write down some Killing-Yano. Of course, I'm not telling you how to map one of these two to another, but you should trust me that there's a triplet in the sense that they rotate under isometries of Killing-Yano tensors, and that means that they satisfy some differential equation. And there's also a singlet. Okay. So one way to think about this is Pauli matrices, right? So there's sigma 1, sigma 2, and sigma 3, and there's sigma 0, which is identity. And if you have Pauli matrices, what you do is you just put them together, you multiply them. So you can multiply sigma 1 with sigma 0. That gives you a particular rotation or some generator. And you can do this keeping a singlet and a triplet. So that means that these Killing tensors are also a triplet. So that means they transform as a vector. As Killing tensors, they are tensors, but they also transform 1, 2, 3 as a vector. Now, I told you also how to construct the operator. You essentially just hit it with two derivatives. And after you hit it with two derivatives, you have a triplet of concept quantities. And indeed, this triplet is the Laplace-Runge vector for the dual black hole. So that's how we constructed. Of course, I've been very schematical, but that's starting from these sort of one forms. It's a complex structure to be precise. We can essentially push that all the way to get a triplet of conserved quantities in this problem. Now we will see in the next lecture, hopefully, that after you go away from the subdual point, two of these conserved quantities are lost, and you end up with only one component of the Laplace-Runge vector, which is what we call the Carter. So that's how it all sort of comes back together to the astrophysical Kerr black hole. You spontaneously break two of these conserved quantities. Okay, so the next part is just some algebra. I'm just going to skip that part, and there's some puzzle about how to get the sort of Carter constant back, and the SL2R and the SL4,2, but all of that, hopefully, together with twistor theory, should be addressed in the next lecture. So thank you.
Oh,
Yeah, we should. Okay, great. Thank you for the talk. We look forward to the next week.
Yeah. Thank you.
I want to go back to